All right, so 150, 180, just based on the problem. 143 and 29, because they're now unique to this problem. Hit enter. And you can see the structure is the same as it was before. Instead of what it was, it's now 143 and 29. Enter, and now we have a percentage. Well, we have it in decimal form, so it's not a percentage, but it is a probability. Now, this kind of question does give us a little bit more context, but not much. It's still very much academic. You're given means and standard deviations. You're not collecting the information on your own. You don't have any skin in the game here. You're not at a point where you're overly interested in the topic. It's not a personal investigation, but at least it's a little bit more than here's two numbers, find a probability. In the context of this situation, we now can actually draw a conclusion, assuming that this information is correct. And I am making that assumption because the textbook that I got it from appropriately cited this information. So I forget where they cited it from, but it was something legitimate. Like, what is it called? AMA, is that a thing? No. What's the medical one? You got USDA for food. Yeah, it is AMA. Okay. All right. I wasn't going crazy. At least not for that reason. The lower bound is always going to be the smaller of the two numbers.
Okay, so we don't look at it. All right.
So even in the curve, the 150 would be here and the 180 would be there. Oh no, don't look at that. You're looking at the x values. Yeah. But what that's telling us, and that's a good point, the height of this is telling us that the 150 is actually more likely to occur than the 180. So each one of these heights represents a probability at a point. But on that interval in between, it's high, it's low to high.
You see how you got that answer? So you're out of the hole when it stops at 230 and it's 303. Point 303.
So that 0.03 represents this area in between the 150 and the 180. All right. Now that 0.303, if you want to evaluate it in context, it means, and I'll just approximate it, about 30% of the population of women have weights between 150 and 180. The problem didn't give units. I mean, we could probably assume pounds, but you don't know. I mean, kilograms would be a little heavy, I think. It's 2 to 1, right? Roughly?
About, yeah.
Yeah. That would be like 30% of the population have weights between 300 and 360 pounds. I don't know. I mean, I'm not an expert, but that seems large. I mean, the percentage, not the numbers. Although they both seem large. I don't know. But again, context. What does it mean? We don't know, because we haven't been provided much context. Where did this information come from? It came from a textbook that was properly vetted, but when was the textbook published? I don't know that for sure, but I know when I typed it out of the textbook, that was in the year 2001. So we're talking about some information that's extremely outdated. So is it meaningful information? By the way, is 30% a good number or a bad number? Are these weights good numbers or bad numbers? I don't know. Are weights indicators of anything anymore? Right? Because when they talk about like health, they talk about weight Or are they talking about things like BMI now? You know, so what conclusions can we draw from this information? My sense would be not much, but at least it's kind of teaching you, at minimum, a small application of some of the stuff that we're covering. All right, and then we're going to see how you can kind of take it and run with it. All right, you can do the same thing with blood pressures. I actually had a student do a project where they brought in a blood pressure machine, and they collected data from the class. Anybody who was willing, you know, they didn't strap them down and force the cuff on them, and do it. Although that would have been hilarious, / a violation of human rights. But you know, it would have been obviously more and more meaningful the more and more people that they can get involved in that. But I mean, that was pretty cool. But you can draw conclusions along these lines with that information. So you know, you never know. So just hopefully a problem like this starts getting the juices flowing. You know, so weights of women. What about weights of men? You know, what was my motivation for choosing weights of women when I typed this problem? Well, that was because I was typing it out of a textbook and they had information about weights of women, but not weights of men. Also, for personal reasons, because I didn't want to have an answer that said, yeah, 97% of the population of men have weights between these two numbers, and my weight was higher than that. I would have been like, yeah, okay, so I'm going to end class now because I'm going to gym. So, you know, like a lot of different possibilities. Anyway, so using the information in example 1, find the score separating the top 25% from the bottom 75%. So that's the same idea as the last page. So I'm going to pop a little star on that one to let you explore it on your own, so that we can dive into something called the central limit theorem. Central limit theorem is really important. Honestly, I tend to think everything I teach in this class is really important because I've stripped out all the crap and I've left only the really important stuff. So central limit theorem is the bridge between the first 2 units and everything that follows in statistics. Right? It allows us to take information about samples and project out to the population. Right? So this is it. This is the missing ingredient that allows us to take what we've learned about graphs, means, standard deviations, and probabilities, and use it to apply that information to the real world. Right? So that you can go, I mean, that example, again, is very simplistic. You know, conclusions, I don't know. But it's at least get you going, it'll get you going in the right direction. This is how we can take that information and actually draw conclusions to a population of farming. All right, so there's something called the sampling distribution of the mean, also known as a probability distribution of sample means having the same sample size. All right, confusing. I'll explain that one in much more detail in a few minutes. What page are we at?
41.
41. Okay, so we're not at the point where we're switching over. The central limit theorem in this part here, assume and conclusion. I'm going to read it, and then I'm going to spend the next little while explaining what it means, because this is not understandable in its current form. At least I don't think it is. Random variable x has distribution with mu and sigma. Right? Well, maybe that is understandable. It's saying that you have a list of values and it's got a mean and standard deviation. I don't know that there needed to be a sentence to leave it to that. Samples, all of the same size, are randomly selected from the population of x values. Right? So now it's starting to get weird. The distribution of sample means as n increases approaches a normal distribution. Therefore, the sample means approach mu, and the sample standard deviation approaches sigma. That's like the WTF part of it. All right. So we'll flesh that out on the next page. And then in short, you could read the in short part, but the in short doesn't make it any better. So not without a contextual situation. We have formulas. These formulas don't help you in the understanding component. You'll need them, or at least to have a sense of them. But that's not the missing ingredient that'll lead to great understanding. All right. This, I think, is. Given a population consisting of the numbers 1, 2, 3, and 4, I'm keeping it simple on purpose because the more values we throw into a population, the more complicated things get. All right. And what I mean by complicated is pages and pages of writing. All right. As opposed to the limited amount of space that I left here, which we can get all what I need to do in here. I can do it in this space, but only for these numbers. If I throw a fifth number in there, now I need the rest of the page to do the work. If I throw a sixth number in, I need a whole blank page to follow. A seventh number, now I need the rest of the packet. All right, it gets crazy quickly. All right, it's exponential like that. All right, given a population consisting of the numbers 1, 2, 3, and 4, find the population mean and standard deviation. Okay, so let's start with that. So I'm gonna make a list. X is 1, 2, 3, and 4. Making sure that's on because I just got through saying how important it is, and I would not be a happy camper if I was not recording. All right, so stat edit. Looks like it's been quite some time since I've been in this stat editor. But I wasn't lying when I said we'd be coming back to it over and over throughout the course, so we are. Yeah, I'm actually only doing it this one time to justify that statement back in September. All right, so the numbers 1, 2, 3, and 4. So I'm going to find the mean and standard deviation of this. You can find the mean by hand pretty easily. Just add them up, divide by 4. Standard deviation, no matter how simple the data is, it's never fun to do. Well, depends on how you define fun. You'd have to have like a warped definition. Stat calc 1. And in fact, for the rest of the course, the only thing that we're using in the calc menu, the stat calc menu, is option 1. Unless you have to take the final exam, you should not be in any of these other functions in the calc menu. Only stat calc 1. I don't have a frequency list, so let me clear that out. So list 1, calculate. So I need the population information here. I'm going to reproduce the entire shebang here. And I'm just going to highlight the ones that I want. You obviously can't copy and paste, so I'm just going to take the ones I want. I'm going to want to reflect back on what the real decimals are, so I want to have them here just so I can look at them and point to them while I'm teaching. But I'm going to make a note in rounded form that the mu, because I'm looking for the population mean, mu stands for population mean, 2.5. And sigma is the population standard deviation, which is, we'll go with 1.118. So, we're going to list all samples of size 2. That's a weird statement, considering I haven't taught you anything about sampling yet. But what that's telling me is if I were to take these 4 numbers and put them in a hat, allowing for repetition, so I guess it would be like a magic hat. I don't know. So you have a hat with 4 cards in it, the numbers 1, 2, 3, and 4. You choose cards one at a time, but after you choose the card, you put it back in the hat, shake it up, choose another card. All right. We want to list out all the possible ways in which you can select 2 cards from the hat. All right. So it's kind of along the lines of a tree diagram, except I'm going to do it as a sample space. So my possibilities would be they could be both ones. I can get a 1 and a 1. I could get a 1 and a 2. A 1 and a 3. A 1 and a 4. And this is going to justify what I was talking about before, where this is why we want to keep it to just 4 values, because you see how it gets out of hand pretty quickly. Maybe I got a 2 and a 1, 2 and a 2, 2 and a 3, 2 and a 4. And we're allowing for the varying orders. So we're thinking of this as a permutation rather than a combination. So I'm not eliminating the 2, 1 just because I got a 1, 2. All right. 3, 1, 3, 2, 3, 3, 3, 4. And then finally, 4, 1, 4, 2, 4, 3, 4.
So sample size, like, try.
Correct. Correct. And that's the connection between the probability stuff and this, because this is really the same as saying, you know, if I had a deck of cards and I was drawing 2 cards at random, what would be my outcomes? It's just on a much, much smaller scale. All right, so we're doing something different here. What we need to do is find the mean for each of these samples. Each pairing of values, they're numerical. I just need to find the average of each pair. The good news is, well, that's not hard, because you're taking 2 numbers, adding them together, and dividing by 2. 1 plus 1 divided by 2 is what? 1. And I get a 1.5, a 2, and a 2.5. All right. And you notice hopefully the progression here, because a 2 and a 1 is really the same as a 1 and a 2, so you can just kind of use that information. And in fact, anything that's a repeat, you could just repeat the calculation. So the first column corresponds to the first row. So you know, even if the calculations were more complicated, I could rely on that. You know, I know that this has to be 1.5. This one has to be a 2. And this one would have to be a 2.5. All right. 2, 2.5, 3. And also, the progression seems to be that going down each column, I'm increasing by 0.5 from the first entry. When you find your averages, you notice that. But then afterwards, you realize, oh, that's just going to be the case. If I know the first number, then I know all of them. Just keep adding 0.5s. So 2.5, 3, 3.5, 3, 3.5, and a 4. So I have all of those means, all those numbers I wrote in black. I'm going to pop all those into my calculator and find the mean and standard deviation for those. All right. And there's going to be one obvious relationship, and then there's going to be one not quite so obvious relationship. All right. I'll just overwrite the entries in L1 because I don't need those anymore. Now, I'm going to just type them in as I have them here, but if you want to be fancy about it, you notice that the 1.5 occur more than once, the 2s occur more than once. You can make a frequency table out of it, but there's only 16 values, so it's not crazy to just type it in individually. I only mention that because if it were a much larger sample size, you know, maybe the numbers 1 through 10 and you had to sample in groups of 5 or 3 or something like that, then maybe you do want to make a frequency table. But of course, I'd never ask you to do that because that would be the whole test. I mean, I think that would be like a semester project, like assigned in September, due like the very last day of classes. All right, so I flubbed something up. This whole talking and typing in numbers, yeah. Yeah, I just put in a 1.5 twice for some reason. I'm just gonna check everything else anyhow. Okay. So I got my numbers in. Stat, calc, 1, just like I did before. My date is still in L1, no need to change that. A little calculation here. And I get this display. I'll get the 1 bar steps in there too. Oh, I didn't do it before, so let me not do that. Not too small, just right. All right, so the first set of data that I had were a set of x values. These were a set of x bar values, all right, because each one of those black numbers were means. All right, each of these are means. They're all x bar values. So when I find the mean, it's really weird, especially when I say what I'm about to say. I'm finding the mean of the means. I have a set of means, but I'm finding the mean of those. But what I'm finding is the population mean of the set of sample means. In this case, 2.5. All right. Now, that's really good news because that's the same as what I got originally from my raw set of data. Same exact number. So what that tells me is if I have a raw set of data and I find the mean of that, so a population, a small population, but even if it was a huge population, I don't need to break it up into little groups, find the average of those little groups, and then find the average of those averages in order to find the average of the population. Right? Just the population average will get the job done. But it also tells me I can go the other way. It tells me that if I know something about the mean within each sample, then I can use that information somehow, and that's the connection that we're going to make. I can use that information to determine what the population is. Because if I can get this, then I know that. You got to start thinking, what's going to be easier to come up with? In this case, it's easier to come up with this because I only gave you 4 data values. But you think about population. First thing that comes to my mind when I think of population is humans. Might not be the same thing that comes to your mind, but I think human population, and then the second thing is there's a whole lot of those. You got a lot of humans. If I needed to find anything related to all of the humans, it's going to be a nightmare / impossible. But it does tell me that if I can find information about small samples of that population, maybe I could use that information to determine the population parameter, that's the word, as a whole. All right, so that's a key ingredient there. Now, as far as the standard deviation is concerned, that standard deviation, sigma, is also of those means. In this case, it's 0.791, approximate. That doesn't look anything like the 1.118. And honestly, it's been on my list of things to do. I know that it works. I have not investigated the underlying theory as to why it works, like the proof that causes it to work. I'm sure it's fascinating. But apparently, if you take your population standard deviation and divide it by the square root of n, so sigma sub x bar would be equal to the population standard deviation divided by the square root of n, you get the same number without doing any of that work. So my population standard deviation was about 1.118. The n represents the number of items in each sample. All right? So this would be, sample of size 2, so that's my n. So I can investigate that really quickly, and I'm using the rounded value. Oh, actually, no, I kept this for a reason, so I could use the whole shebang. 1.118033989 divided by the square root of 2. That decimal is the exact same thing as that decimal. All right. So what that's telling me, and again, this approach here, this is all me. Like this whole listing out sample, it's my way of understanding it, and I figured if it helped me, it might help others. It doesn't always work, but that's the point. I have no idea what the justification is for this step. I just know that it works. All right, it's on my list of things to do. But that also is a connection. It's a relation between the sample, they call it the standard error of the mean, but it's also basically saying the standard deviation of all of those sample means. It's a connection between the two things. So they give that formula in every textbook that I've ever seen, but I look at it slightly differently. Because if that relation that I wrote in green is true, then this one must also be true. And that's the missing ingredient. That's the connection. That allows us to determine a standard deviation for the population if I know something about the standard deviation for each of the individual samples. All right? So our job when we collect data for studies, whether it's in a classroom or for a job or real life, would be to get this number so we can draw a conclusion about this number. All right, because you collect data. If I were to get blood pressures of all the people in this class, the only thing I can do at this point would be to say, all right, people in this class have blood pressures in the normal range. Cool. Have I advanced anything in the realm of humanity? No. I don't know. But did I need statistics for that? No. I got a chart that says what's normal. I got numbers on the machine. I don't even know how to do it manually. Like when they put the little stethoscope on my arm, I don't know what they're listening for. They put the little thing on my finger. They do that at the same time. I don't know why. But I know somehow the machine does the same thing. But I don't know what it's doing. I know that it squeezes a lot, then it lets off, then it gets a measure, and then it lets off a lot faster. I don't know why. But I know it gives a number, and that number is either good or bad. I've not advanced the cause based on doing any of that. This allows us to advance the cause, because what it does is it takes all that information that I've drawn from this group, and it allows me to project it out to maybe all of WCC, all of Westchester County, if we're a representative enough sample, maybe the entire United States, maybe just the Northeast. I don't know, but it allows us to go broader rather than just staying within the focus of this class. Right, and that's powerful stuff.
So on a test, step one, it goes straight to the formula and skip number two, right?
Oh yeah, this is understanding what the concept is. We haven't even gotten into like questions and stuff. So. Yeah, the questions, I mean, they're pretty basic, because the comparison between not central limit theorem and central limit theorem, you look at what's similar and what's different.
I'm just having trouble like figuring out like size 2. Like what,
Where did that come from?
Yeah, just because it's making me think like to be looking into like a second column somewhere.
So the samples of size 2 is just telling us that when we draw samples from our population, how big those samples should be. And then once we have that, we're good with that information, and then that's the end of it.
Oh, okay.
Yeah, so I could have gone samples of size 20.
Nice.
In this case, not 20, but you know.
Oh.
But you know, like if I were dealing like the blood pressure example, if I were actually polling individuals from the college, probably don't want to break them up into groups of 2, because then I would have like 1,000 groups of 2, groups of 100 maybe, and then my n would be 100. But that's the connection between permutations, combinations, and this stuff, because it's like, well, how do you break them up into groups of 2 or groups of 100? Do I want them in the form of a permutation or a combination? All stuff that we'll address.
So you're saying try to do it in one group, not a lot of groups?
Well, that's the thing. Mathematically, so in a math classroom, you could do it with one group, and then use that information to project out. But you could have extreme variation within one group. I mean, with blood pressure, it's entirely possible, although very not likely. I can randomly select 100 people and get 100 people who have hypertension. So I'm going to draw a conclusion that the entire United States is filled with people with hypertension. 100%. Not true. It may not be far from that, but not true. All right. So do we want to do it just once in real life? Probably not. That's why it's not a focus group. It's focus groups. You know, they don't just get a sample of 10 people, put them in a group in a room, and get their opinions. They don't do that just once. They do it like 20 or 30 times, so that they can eliminate any kind of extreme cases. All right. But in a math class, to get an answer on a test, just once is all you need. All right. So example 1 is saying find the probability that the score is above 140 given 143 and 29. So very streamlined example, just the nuts and bolts. This is telling us to find the probability that the x value, so the score is x, is above 140. So I would do a normal CDF. $140, I'd pop in something large with a mean of 143 and a standard deviation of 29. All right. On a test, that's perfectly fine. You write 140, comma large. You don't have to tell me what the large values were. You know, when we were doing it before, I used 100 and 101 just to show that there was no difference, but that was only for my benefit. So this is what I would do here, 140, something large. Now, I used 100 before. Well, 100 in this context is not large, because my lower number is 140. So I need something large relative to the 140. So now maybe we go 1,000 or 10,000. I still have the 143 and 29 stored from before. I don't need to change that because I'm working with the same parameters. Paste it in, hit enter. and then I do the same thing, just with something slightly larger, or maybe a lot larger. I'll go to 1001, just to see if there's any movement on my decimal. It's the same decimal, so I know that I have my answer. All right, so about 0.541. And you can just use a regular equal sign, that's fine there, as long as you follow the rounding instructions. All right, so that's where we were. That's not central limit theorem. That's why it looks so familiar. That's just a percentage question, percentile question. Here's where we're looking at something that is central limit theorem. Two slight differences, but they're conceptually massive differences, but in terms of the structure of a question on a test, they don't look very different at all. All right. This time it's find the probability that the mean score, so now it's an x bar instead of an x, and they also give us an n. All right. So the question now is p of x bar greater than 140. So we're looking at normal CDF 140 to something large. Now, I need to put in two pieces of information. I need to put in a mu sub x bar and a sigma sub x bar. All right, the whole point behind that exercise was to know that whether I'm dealing with an individual score or a set of averages, the means are not going to change. All right, so mu and mu sub x bar will always be the same thing. So they gave us a mu. Here's my mu. That's going to be the same as mu sub x bar. I can just pop that right in. I don't have to give it a second thought. 143. But if I need a sigma sub x bar, I have to take whatever the sigma was and divide it by the square root of n. All right? So this is a case where you had a population, you broke them up into groups of 100, just like we did here, except each one of these groups had 100 values in it. You found an average from each one of those 100 value groups, and then found the average of all those averages. So the question would be, what would the standard deviation be then? The answer would be, it wouldn't be easy to find. However, if I know that little nifty relationship that tells us that sigma over the square root of n will give me the same thing, and sigma is 29, and the square root of n would correspond to the square root of 100, then I have what I need. All right? So, if you're into just getting stuff right on the test, it's Saturday morning. Sometimes that's all we want. We'll worry about learning later. Look at the difference. X bar, same, different. Similarities and differences. That's all you're looking for. So, bars. Second bar, sorry. Wrong course. 140 to something big. I'll keep it at 101, 1001, it's fine. I don't want 29 anymore. I want 29 over the square root of 100. You could just put 29 over 10 or 2.9. I'll write it as the square root of 100. Because you can't always count on it being a perfect square. So you get that. And then do it again with some really different, but I like to go bigger. Go bigger, go home. Same decimal. I'm going to go out to 4 decimals here so I don't overround. 0.8495. All right. So there are some implications as to why these numbers, these final answers are so massively different from one another. But it has to do with the fact that now you're dealing with samples and averages and measures of center. So the key ingredient here is the idea that you're going from the individual to the group, right? So if you're talking about sampling just a single person, you could have wildly different values for heights, weights, blood pressures, body temperatures, maybe not so much body temperatures. We're all generally in the same region there, unless you're talking about like living versus not. But you're really just kind of looking at the individual and saying, I mean, I could be, you take a person from out in the hall that I haven't seen before and bring them in, you don't know what you're getting. So you could be getting a kid, you could be getting an adult, a whole lot of different possibilities. So the heights and weights could be all over the place, right? Now, if I were to take a group of 100 people and average all their heights, for example, together, I'm going to get a number that represents the average height of that group. Then I take another sample of 100 people selected at random, average all their heights together. What I'm doing is I'm eliminating all the extremes, all the really high numbers and all the really low numbers. I'm bringing it all to the center. So where on an individual level I might have a lot of movement from person to person, from group to group, I'm not going to have a lot of movement. There's not going to be a lot of variation. So my standard deviation, which is a measure of spread, very spread out. 29 units of spread here, 2.9 units of spread here. All right? That impacts the probability severely. All right? So that relationship is a key ingredient to the central limit theorem, because now instead of looking at the individual, and it doesn't really make sense to look at the individual, it makes sense to look at the group, because if I'm trying to draw a conclusion about a population, I'm not doing it one person at a time. I'm doing it whole groups at a time. All right? For simplicity, but also for the mathematics of it. And also, I'll show you something really, I think, pretty cool. So we had all this information here. I put it into L1, right? This information, if I were to graph it, it would be a uniform distribution. Each one of these values occurred once. So if I created a histogram out of it, the bar for 1 would be the same height as the bar for 2, the same height as the bar for 3, and the same height as the bar for 4. All right, so let's actually take a look, and I'll just do it really quickly, because it's not really a matter of creating the graph as much as seeing the outcome. Let me look at the histogram for this information. So this goes from 1 to 4 by half units. I'll go from 0 to 5, just to have some wiggle room on either side, by half units. And I don't need to go anywhere near as high as 10, so let's go up to like 3. I'll go to 4. All right, so my original data was uniformly distributed. Each one of these occurred once. So if I made a histogram out of that, it would be a flat bar across the top. This one looks like, if I were to make a curve out of this, it would look like a normal distribution. That's what happens with the central limit theorem. It takes any distribution, uniform or otherwise. If it starts off being horribly skewed, bimodal, so 2 big humps, maybe it's just scattered all over the place. It could be uniform, it could already be normal. But once you apply the central limit theorem, break it up into samples and find averages, the distribution, if I create a graph of all those averages, will always be a normal distribution, which means that normal CDF stuff will always apply with no exception. That allows us to take techniques involving the empirical rule, normal CDF, inverse normal, and apply it anytime we use a central limit theorem. All right, so breaking it up into groups not only makes sense in context, but it also makes sense mathematically, because it allows us to do things involving probability where otherwise we would not be able to. All right, that is the missing ingredient, because if I can establish something that was not normal into something that is normal, I've just changed the rules of the game. And that is a rule that we need to have in place in order to do any of the things that we're going to learn about moving forward. All right. The next example is more in context, but it's really the same stuff. It follows the same structure. A corresponds to example 1. B corresponds to example 2. So I'm just going to put a star on that. This is page 42.